Those are online. Are you able to hear me?
Yes, sir.
Okay. Well, just give me 5 minutes time. I have an important call to take. Okay. Keep revising the topics of yesterday. I'll come and discuss about the LC oscillations and transformers. With that, we are done with this chapter. So, yeah, is it clear to people who are online? I'll just be back in 5 to 10 minutes.
Yes,
Have
sir.
a call. Okay. Please.
Yes, sir.
Sir, you are not audible.
Yeah, those who are online, are you able to hear me now?
Yes, sir.
Okay. So first we'll start with transformer, okay, because that's a slightly lengthy topic. Once transformer is over, then we can discuss LC oscillations. Now listen. Write down the heading as transformer. So what is a transformer basically? So if you see, there are certain places where the voltage comes out to be high. If the high voltage needs to get converted to low, or you need that voltage to become even more high. Means, in simple terms, if you want to either bring down the value of the voltage or take the value of the voltage slightly higher, then we use an intermediate device called as a transformer. So what is the work of a transformer? Is basically to convert voltage from a particular value to another value. It can be a low value or a high value. Okay. So it is an electrical device. It is not an electronic device. It is an electrical device which is used for converting only alternating current. This is an important point. Okay. So a transformer is basically an electrical device which is used for converting an alternating current at low voltage into that of a high voltage, or vice versa. Means the reverse also can happen. Okay. For converting an alternating current at low voltage to a high value and vice versa. So basically, compared to the input voltage, if the output voltage is higher, I repeat it, compared to the input voltage, if the output voltage is higher, that kind of a transformer is called as a step-up transformer. So if a transformer is able to increase the input voltage, it is called as step-up transformer. At the same time, if it decreases the input voltage, it is called as a step-down transformer. Done? Done? Okay. Now, the question is, whenever you have any kind of an electrical circuit, then you need a particular principle on which it works. Okay. So you need a particular principle on which works. It is basically working on the principle of mutual induction. So I repeat it. Transformer works on the principle of mutual induction. So what is mutual induction? You already know this. What is mutual induction? If there is a change in flux taking place in one of the coils, then there will be an EMF induced in the neighboring coil. So same logic. So when you talk about those things, wherever the flux is changing is called as the primary coil, and the place where the EMF is induced is called as the secondary coil. You remember this, right? Now, the construction here is, one minute. Now the construction is basically a transformer consists of two coils logically. When you want mutual induction, you need more than one coil. So out of the two coils, one is called as the primary, and the primary is the one which is connected to whom? Primary is the one which is connected to the alternating source. Okay. So A transformer essentially consists of two coils of insulated copper wire. What do you mean by insulation? Something like this. So inside that you will have copper wire, on top of which you will have insulation, having different number of turns and wound on the same soft iron core. So I want to recollect one point here. If you go back to the 5th chapter, we discussed a concept called as retentivity and coercivity. You remember this? You remember these terms? So what does retentivity mean? It is a property of an iron to retain magnetism even after the removal of external magnetic field. Is that right? So that property is called retentivity. So when you talk about the different kinds of materials which have different retentivities, one is called as a soft iron core and the second is a steel material, which is a hard iron. So soft iron core generally have less retentivity and less coercivity. So if you see, why are they even using soft iron core and not a steel? Because if you go back to the basic and see, what is the work of a transformer? The work of a transformer is to convert voltage from one value to another. It can either be lower or higher. Does it have anything to do with storing magnetism in it? Obviously no, right? So since it does not need to hold any magnetism within itself, we ensure that the core that we are using is having lesser retentivity. That is the case. What kind of a material am I supposed to use? Obviously, a soft iron core. The reason why I told you is they'll ask you this question as a 1 mark. So generally, when it is a 5-mark question, right, you will not have 1 5-mark question. So 3 marks will be for the explanation part, 1 problem, and it can be 2 1 marks or 1 2 mark. So in those, if at all it is 2 1 marks, right? One of that I've seen most of the time they ask this question: why is it made of soft iron core? Because we don't want the material to store magnetism in it. That's not what we are concerned about. Is that right? So the coil P to which electrical energy is supplied is called as the primary, and the coil from which the energy is drawn or the output is taken is called as the secondary. Okay. To prevent something called as, 1 minute, I have some problem. Yeah. So to prevent energy losses due to eddy currents, forget about eddy currents as of now, I'll tell you what it is. So eddy currents means, remember, as of now, they're circular currents. Eddy are basically circular currents. What do we use? A laminated core is generally used. I repeat it. To reduce the energy loss due to eddy currents, what do they do? The core that is used. What is the meaning of core? Core is the outer structure. Okay. If you look at the diagram, there are 2 kinds of transformers that we have drawn. Right. One is called as step up and the second is called as the step down. Because what is one of the important points that we learned? The number of windings in the primary and the secondary are the same or different. I told you here. Consists of 2 coils having different number of turns, but they are wound on the same soft iron core. Is that what is happening here? Right? Is that what is happening? Look at the cursor. So you have a primary coil here, okay, which is connected to the alternating source, and the secondary coil is the one from where the output is taken and connected to the load. Load can be any resistive element. Okay. Now, so this core is there. No, this core is what is called as laminated iron core. Why are we using it? To prevent energy loss due to eddy currents. Yes. Okay. Because of high permeability of soft iron, what will happen is, though you are using soft iron, its retentivity is less. So try to understand. Retentivity means it cannot retain magnetism, but at the same time, its permeability is very high. What do you mean by permeability? The allowance that it gives for the magnetic field to pass within itself. That is going to be high. You cannot control because it's a ferromagnetic substance. Is that clear? So it has high permeability. What will happen is the entire magnetic flux that is linked with the primary coil will get connected to the secondary coil. In the sense, when the alternating current is passing through it, right, what will happen to the direction of current in this? So what will happen to the direction of current on the side P? It keeps changing. When the direction of current is changing, what will happen to flux? That will also change. And due to the change in flux that is taking place only, there is an EMF induced to the neighboring coil, that is the secondary coil. So try to understand the point here. Whatever flux is getting linked with the primary coil, we need to ensure it is completely linked with the secondary coil, or else what would have happened? The amount of EMF that will get generated on the right side will not be sufficient enough. So the first thing that you need to ensure when you're designing this kind of a circuit is need to ensure that the whole flux linked with the primary coil is getting linked to the secondary as well. And that is why we are using, that is why the winding is done on the same iron core. Is that clear, guys? Okay. So due to this, what will happen is due to the laminated current, there will also be prevention of stray currents. Stray currents in the sense the current which is getting leaked to the surroundings. Okay. So it also prevents from the stray current being generated in the conductors lying around, hence reducing the power loss. So what are the three things that are happening? One is you are preventing the energy loss due to whom? With the help of laminated iron core. Second is you're connecting both the primary and the secondary coil on the same soft iron, so that you're trying to ensure that 100% flux is getting linked between both. And the third one is, what are you doing? You're trying to prevent the stray currents, which in turn reduces the power loss as well. Have these 3 points in mind. Based on this only, we're going to derive the mathematical expressions. Is it clear, guys? So if I have to give the whole process in one block diagram, right? If I have to give it in one flow chart, then I will say alternating current is creating an alternating flux in whom? In the primary coil. I repeated, alternating current is creating an alternating flux in the primary coil, and the alternating flux is getting linked with whom? The alternating flux is getting linked with the secondary coil, and from the secondary coil, what is getting generated? You're getting an EMF, and what kind of an EMF is that? That is also alternating in nature. So the EMF that is getting generated at the secondary end is also alternating in nature.
So what is S linked with this?
S is secondary.
Okay.
Okay, that's what is given in the working. I've just given it in one step. I've given it in one step. I hope you understood. No, this is the whole working process that is explained. Okay. Now we'll see what is the theory that is associated. So since it is theory, there are certain assumptions that are done, which does not happen in the real-time basis. So write down the heading as theory. So this is important. Okay. But before that, I suggest you to draw this diagram. Are you able to see? Fine. These are two different kinds of bindings. So this is a separate transformer, this is a separate transformer. Okay. Shall I proceed? Done. Shall I proceed? So, theory. Okay. So, you have drawn two diagrams, right? In those two diagrams, if you see, the secondary one is open. The secondary coil is open, means it is not connected to any load. Is that right? So, the derivation itself starts with this concept. So, you are considering the situation where no load is connected to the secondary, means its terminals are open. That is the first point. Okay. So, when the terminals are open, then we can say the number of windings in the primary coil, I take it as N1, and the number of windings in the secondary coil, I take it as N2. Is it clear? Okay. Then, what is going to be the flux, that is, what is going to be the value of EMF that will get generated in the primary coil due to the change in flux? So, remember one fact that within the primary coil also, what is happening? Alternating flux is generated. So, when alternating flux is there, EMF is generated. So, what does Faraday's law tell you? E1 is equal to minus N1 into d phi 1 divided by dt. Then what about E2? Minus N2 into d phi 2 divided by dt. Is that right? Okay. Now, here I need to make a small change. Can you tell me what is it? From the beginning, I've been telling you one point. What is it? Both the windings are connected to the or wound around the same laminated core to ensure what? To ensure that the flux that is created at the first winding is completely linked to the second winding. So when that is a scenario, is there a question of d phi 1 and d phi 2? What should have been? It should have been only d phi by dt. So the correction is it should be d phi by dt. Is that point clear? Now what I will do is I'll divide both. When I divide both, E1 by E2 will be equal to N1 by N2. So what is E1? The potential difference that is occurring across the primary. E2 is the potential difference across the EMF across the secondary. N1 is the number of windings in the primary and N2 is the number of windings in the secondary. Now going back to the definition of step up and step down transformer. So what does a step up transformer tell you? So step up means, so for it to be called as step up, what should be the relation of between E2 and E1? E2 should be greater than E1, which implies E2 by E1 should be greater than 1. But what is E2 by E1? It is N2 by N1 from this equation. From this equation, it is N2 by N1 is also greater than 1. So what can I say? N2 is greater than N1. This is point clear. So what am I trying to say? If you want to design a step up transformer, then you need to ensure that the number of windings in the secondary coil is more compared to the number of windings in the primary coil. Similarly, if you want to design a step down transformer, what are you supposed to do? Do the reverse of it. Just do the reverse of it, you will get the answer. Am I clear with this? Is there anyone who is confused? This is a very, very, very important topic with respect to this chapter. Clear up? Okay. Suppose I am taking EMF across the primary coil to be E. Okay. By Lenz's law, what can I say? There is a self-induced EMF E1 that is getting generated. That's what we wrote, E1 by E2. Correct? So what will be the relation between E and E1? I repeat the question again, listen to this carefully. This E stands for the instantaneous EMF that is getting generated by the alternating source. What is E1? E1 is a self-induced EMF. You remember self-induction? So what happens in a self-induction process? What happens in a self-induction process? There is a change in flux taking place within the same coil, then EMF is induced in it. Correct? So that self-induced EMF, I'll call it as E1. Now what will happen is this E1 that is getting generated at the ends of primary coil will oppose the cause, that is E. Why? That is according to Lenz's law, right? In such a way that the net EMF now is not going to be E1 or E, rather it will be E minus E1, which I will call it as I1 into R. Means the net EMF that is getting induced due to the AC source itself plus the back EMF. That is a self-induced EMF. So when I say plus, why did I put a minus sign? Because it's called as back EMF, it gets generated exactly in the opposite direction. So E minus E1 will be equal to I1 into R. What formula? What did I apply? I applied basic Ohm's law, right? I1 into R. Now, this EMF, the net EMF sends the current I1 through the primary coil of resistance R. But in general, in reality, what will happen is you're taking that winding. So what is that winding made up of? Copper, which is insulator. That's what we told. The windings, the resistance is generally very, very, very low. In such a way that I can ignore the term I1 into R. If that is the case, then I can say whatever is the EMF that is connected, the alternating source that is connected across the primary coil will exactly be equal to the induced EMF E1. That is why there we could write it as E1 by E2. Breathe up. So this is another important point that we need to make a note of. Okay, E will be equal to E1. From this, what you can conclude is, if you take E1 to be the input voltage, E2 can be considered to be the output voltage. Hence, that formula E1 by E2 is equal to N1 by N2 holds true. Is it clear? Right? Next. The next point is, you have this N2 divided by N1, right? Not N1 by N2. You have N2 divided by N1, that is the number of turns in the secondary to that in the primary, is also given a name called as turns ratio, or it is also called as transformation ratio. Sometimes what they will do is they will give you the number of turns and then ask you to find the turns ratio. So you should not get confused. Turns ratio, name itself is suggesting ratio of the number of turns. But the point to be noted here is, what should be the numerator? N2 should be the numerator. If you write N1 by N2, it is not called turns ratio. So turns ratio basically represents output, that is N2 divided by N1. On the point note. Is it clear? So if that is going to be the scenario, then in the case of a step up transformer, what will be the turns ratio? Is it going to be greater than 1 or less than 1? Greater than 1, because N2 is greater than N1. Whereas with respect to a step down transformer, it is obviously going to be less than 1, right? Now, this equation is there, no? So this is actually not an 100% accurate equation or a relation. It is derived under certain assumptions. Okay. Then what are the assumptions? They will ask you these things also. What are the assumptions considered in a transformer to derive the turns ratio? Okay. The first thing is, what is the first thing that we did? How did we get E is equal to E1? What did we ignore actually? We ignored the primary resistance. So primary resistance and current are considered to be small. That is the first point. So write down the heading, write down the subheading as the three assumptions under which turns ratio is derived. So what is the first thing? Primary resistance and current are small. That is the first assumption. Second, so what did we say? The same flux is getting linked between the, because you remember I told you not d phi 1 by dt and d phi 2 by dt. What did we change it to? D phi by dt means the same flux is getting linked between the primary and the secondary. That is second assumption. Though in reality what will happen is there will definitely be flux leakage. You cannot control it. Okay. Second assumption is the same flux links both with the primary and the secondary windings, and the flux leakage from the core is negligibly small. Am I clear with both? What is the last assumption that we have taken? So I told you the derivation itself starts like this. What is it? The secondary coil is open. Means you did not connect any load across. So the third assumption is the terminals of the secondary are open, or the current taken from it is very, very small. Okay. So we derived the relation for the ratio of EMFs and the number of turns. Is that right? So E2 by E1 is equal to N2 by N1. But now we will try to derive the relation between currents in the primary and the secondary coil. Though we told the currents are negligible, you cannot take it to be completely zero also. We need to find a relation, like how the value of current is related to the number of turns. Because in the equation where E is equal to E1 is there, no. There, it is because of resistance I told the whole expression can be ignored. It's not because of current that I told. Okay, having that in mind. So currents in primary and secondary, there is an assumption. The assumption is it is an ideal transformer. So when you say a transformer is ideal, it is 100% efficient. That is the first thing. Ideal basically means something which is 100% perfect, which is not possible at this point. So that's called as an ideal scenario. So when you say the transformer is ideal one, then the first thing that you can assume is energy loss is zero. Means you're trying to say there is no energy loss at all. When there is no energy loss, I can say there is no power loss also. If a power loss illana, can I say input power and output power should be the same? Correct? But what, so input power is equal to output power. Under what assumption, guys? I repeat it again. Under what assumption? Considering the transformer to be an ideal one. Okay. Input power, basically what is the electrical power? How is it defined as? It is defined as the product of EMF and current. So E1 into I1 is equal to E2 into I2. Is that right? Right? Where I1 and I2 are the currents in the primary and secondary respectively. Where I1 and I2 are the currents in the primary and secondary respectively. When E1 I1 is equal to E2 I2, what can I say about I1 by I2? I1 by I2 will be equal to E2 divided by E1. Is that clear? But what is E2 by E1 already? N2 by N1. So can I say this is equal to N2 by N1? Means the EMF is directly proportional to the current, directly proportional to the number of turns, whereas current is inversely proportional to the number of turns. Okay. So from here there is an important conclusion that we can draw. Is there any confusion there still here? Because we discussed so many things. Any confusion till here? I didn't get you. OE2. Okay. Is this fine now? Okay. Now, if you see, basically, what does a step-up transformer do? Step-up transformer will increase the voltage but decrease the current. Right? So that's what has happened here. A step-up transformer basically steps up the voltage, but at the same time steps down the current in the same ratio. Secondly, you have a step-down transformer. It steps down the voltage, but steps up the current is exactly the same ratio. So from this, what we can conclude is, we can define a parameter called efficiency of this transformer. What is efficiency? Efficiency basically means output by input. Efficiency, basic definition, it is output by input. Whatever is the suffix you are going to add, that you can add. So here it is what? Output power divided by input power. So if I write it as only output power by input power, you call it as fractional value. If you multiply it with 100, you can call it as efficiency. Okay, it is a percentage value. So what happens in real time is, what did we assume? Actually, we did that I1 by I2 under the concept that a transformer is 100% efficient, but in reality, no transformer can be 100%. It is rather efficient somewhere between 90 to 99%. 99 is also a tough task. Okay. Is it clear till this step? So if you see from the beginning, if you just give a run through, the first point is we try to understand what a transformer is. So transformer is an electrical device which changes the value of voltage, value of the input voltage. It will either increase or decrease in pivot value. Low to high or high to low. What about the principle? It works on the principle of mutual induction. Third, what about its construction? It is made up of an insulated copper wire where one of the windings is connected to the alternating source and the other one is connected to the load. And both are wound around the same soft iron core. Why do we use a soft iron core? To ensure it has less retentivity. But definitely you cannot neglect the permeability of it. It has a high permeability, based on which there will definitely be some losses that are going to happen. Is that right? So we'll try to prevent it. That's a different story. Then what is the working of it? In the working, what did we see? Alternating EMF will generate. I gave you that block diagram, that flow diagram. Alternating EMF will generate alternating flux. Alternating flux will induce EMF in the secondary coil, and the EMF will be alternating in nature. Right? This is how it works. Right? Then we saw the theory part. In theory part, what is the assumption with which we started? That is for the power loss.
Secondary is not connected to load.
Yes. So you started with the concept that the secondary is not connected to the load. When the secondary is not connected to the load, we derive the expression E1 by E2 is equal to N1 by N2. That is the theoretical part. Then we try to derive, so N2 by N1 is called as turns ratio, or you call it as transformation ratio. In the next part, we try to derive the relation between current, EMF, and the number of windings. So for that derivation, what is the assumption with which we started? A transformer is 100% efficient. Right? It is an ideal transformer. Then we got I1 by I2 is equal to E2 by E1 is equal to N2 by N1. So they were in the inverse. They were inversely proportional to each other. Then what are the three assumptions we took for the derivation of all these things? The resistance and the primary current are small, secondary. Same flux is linked with both primary and the secondary coils, and we have ignored the flux leakage with the surroundings. And the third part is, sorry, terminals of the secondary are open. Means, so that is the starting part of the derivation, right? And the last part that we saw is the efficiency. What is the efficiency? It is defined as the ratio of output power to the input power multiplied with 100. And what is the scenario? Like a transformer can be somewhere between 90 to 99% efficient. It cannot be 100%. Right? So with all these points discussed, now we will come to the real-time scenario of what are all the different kinds of practical losses that can occur in the transformer. Shall we look at them? So the first one is called as copper loss. The name itself is suggesting this. So first one is called copper loss. What is copper loss? What is the material you are using? Copper. So copper is basically a conductor. When you pass the current through a conductor for longer duration, what will happen to it? You get heat. Heat is a form of energy only, no? So some energy is lost due to the heating of copper wires, which are used in the primary and the secondary windings. Right? But how can you reduce it? So the question is not about why the loss is occurring. The loss will occur because it's a real-time mission. It will occur. But as an engineer, how are you going to prevent it? Is what the question is. So you will use a laminated iron core, right? And also, sorry, this is not here. You cannot use laminated iron core. That is for the flux leakage. So here, what you can obviously do is you use thicker wires of copper, right? When you use thick wires, what will happen to the resistance? We know that R is equal to rho into L divided by A. Thicker wires have lesser resistance. So lesser resistance used to this formula, what will happen to it? So I square R. So when R is less, that is why you remember in the derivation also we told the resistance is lesser. That is why we ignored that value I1 into R. Remember? So there is a logic that we get connected. So how can you? So there are two kinds of questions that they will ask you. What are the different kinds of energy losses and how you prevent it? The first loss is copper loss due to the copper wire heating of current will take place. And how are you going to prevent it? Obviously by using a thick copper wire. Secondly, what is the loss you're going to have? You will have eddy current loss. So eddy current is generated. It is because of the, you remember the flow chart? In the flow chart, what is the second step? So first step, alternating current, and what is getting generated? Alternating magnetic flux. So alternating magnetic flux will keep creating eddy currents. So eddy currents, I'll explain to you. It's only a 10-minute concept because I don't think I can do it today. But have this in mind. Okay, eddy currents mind. Why is it happening? Because of the alternating magnetic flux, which induces eddy current in the iron core, which leads to some energy again being lost in the form of heat only. Wherever current resistors are getting involved, definitely there will be heat loss. But how can you prevent the eddy current loss? First step itself we saw by using a laminated iron core. So another we are using a laminated iron core. Breathe. Next, you need to have this in your mind. Though we are using a soft iron core, we can't forget the fact that it is a ferromagnetic substance. Whenever ferromagnetic substance is introduced to an alternating magnetic flux or alternating magnetic field, what will happen to it? There will be a process of continuous magnetization and demagnetization. And what do ferromagnetic substances exhibit? They exhibit something called as hysteresis. Yeah, hysteresis because of the retentivity and coercivity. The graph is not a straight line. You remember that kind of a shape will come. So that shape is actually called as the hysteresis curve. So hysteresis is not very word later. It basically means lagging. That's it. One is lagging behind the other is what as a technical name of hysteresis curve. Is it clear? So what has happened? Recollect the sequence. First, what kind of an iron core are you using? Soft iron. Soft iron is basically a ferromagnetic substance. So out of paramagnetic, diamagnetic, and ferromagnetic substance, which materials will exhibit hysteresis? Is it paramagnetic and ferromagnetic or only ferromagnetic? Only ferromagnetic. And don't forget, iron is a ferromagnetic substance, due to which there is a continuous process of magnetization and demagnetization taking place. And during this process, what will happen is work is done in each cycle. You're doing some work in the process of magnetization and demagnetization, and that work is obviously going to get converted into some amount of heat. Breathe. Is it clear? But how are you going to prevent it? Okay. So obviously, how can you prevent it? By choosing that soft iron core which has low retentivity and low persistency. Means the graph should be as narrow as possible. Are you guys able to visualize what I'm trying to say? The graph B and H core graph, we do it. We draw something like this. Remember? So you need to ensure that the curvature is small, means it should be a narrow graph. When you're able to choose that kind of an iron core, yes, you can prevent it. Can you avoid it 100%? No. Prevent it. You can reduce it to some extent. Yes. Prida. And one more assumption that we did. What is it? Flux leakage. Is there a possibility where you can avoid flux leakage? Okay. So the magnetic flux produced by the primary coil may not be fully associated with the secondary coil. It might not happen. But at the same time, what will happen is there will definitely be a flux leakage that is taking place into the air medium or whatever is surrounding. Generally, you will have air only. You will not take a transformer and put it in water. Right? Obviously, you will have an air medium. So it is generally going to happen. There will be a leakage that is going to take place. Right? But how are you going to minimize it? By trying to wind the primary and the secondary over each other. So I asked you to draw two diagrams. In that, look at the second one. So first diagram appeared. First diagram, the primary was on the left, secondary was on the right. Whereas in the second case, the primary and the secondary are wound over each other. Right? So that is one of the reasons or one of the ideas of reducing the flux leakage. Okay. So these are the four important concepts that are there. And the last one is, see, it is an extra point that I have added, which is called as humming loss. Name is suggesting. So till now, the energy was lost in the form of heat or leakage, flux leakage. Humming, name is telling sound. Right. What can happen is, so generally when the transformer works, right, whenever it's working, it gets heated, and the materials are metals actually. So metals, what do they happen to them when heat is subjected? They expand, right? So its length keeps changing. So during the process of magnetization and demagnetization, what will happen is there will be an increase in length and decrease in length taking place, and this process is basically called as magnetostriction. It's called magnetostriction. And due to the increase and decrease in the length that is taking place, what is happening is there is a humming sound that will get generated. Okay, and it is lost in the form of, obviously in the form of sound. I have not given the prevention measure. If at all you need to reduce sound, what are you going to do? Use some acoustic material. That's it. You know what is an acoustic material, right? Something which absorbs sound so that you cut down the reflections. Especially the concept of reverberations and echoes being cut. It's actually not a part of your textbook. So when for exam point of view, only the first 4 points will be tested, but this is for your knowledge. This is also there. There are few more also that will happen, but we don't need them at this point. I hope it is clear. Right? This is all about transform. And there is nothing for me to tell you why a transform is used, because that is the discussion with which we started our concept. Correct? So the next two topics that are left out are LC oscillations and eddy currents. Eddy currents that I teach, I forgot in the previous one. I'll explain in this chapter. Okay, but we'll see. LC oscillations, both are theory only. It's a very simple thing. After class, we will finish it off. Okay. Then we'll go for the paper discussion, which I told you. Surya. Any other doubt? Here. So those are online. Any doubt, guys?
No, sir.
Okay.
No, sir.
Wind up.
Sir,
Yeah, tell me.
sir, with this chapter, term and portion is over, sir.
With this chapter?
I mean, book one. I mean, the book one is over
No.
with this, sir.
No. Book one, illa. Book one, there is one more topic that is pending. Electromagnetic waves, 8th chapter. That is maximum 1 class or 2 classes.
Okay.
That's a very, very small chapter. Seriya, we'll wind up.
Thank you, sir.